Section 4, trig functions are used to solve right triangles. Angles of elevation are measured from a horizontal line up to the line of sight, and angles of depression are measured from a horizontal line down to the line of sight. Quick illustration here. If we're standing right here, this is the ground as our horizontal line, looking up at, say, the sun over here. Our angle elevation is our angle from the horizontal line up to our line of sight. So whatever angle we measure from the ground, from a horizontal line up to the sun. Here, we might be standing on top of the roof, looking down at a parked car over here. We'd have an imaginary line straight out here, and we measure our angle of depression from that horizontal line down to our line of sight. Those two angles are used in a lot of our word applications of our trig problems here. So they're used to solve some of our right triangles. We'll come back to those in our word problems. Our first one here says solve the right triangle ABC if A is 34 degrees and 30 minutes and C is 12.7 inches. You can see that information labeled in our diagram here. Once again, reiterating the fact that C is typically our right angle. So looking at this, if we want to, when we say solve the right triangle, that means solve for side A, solve for side B, and solve for angle B. So the easiest thing to do to start with, I think, is probably angle sum of a triangle is 90 degrees or 180 degrees. 90 that's taken up here, so 90 makes up the other two. So angle B is simply 90 degrees and 0 minutes minus 34 degrees and 30 minutes. Going the long route here, I have 89 degrees and 60 minutes. So 60 minus 30 is 30 minutes, and 89 minus 34 is going to give us 55 degrees. So angle B is 55 degrees and 30 minutes. Now, we can solve for side A or B. It doesn't matter how we start, but let's say we want to solve for side B. So in relationship to the angle it's given, 34 degrees and 30 minutes, side A is the opposite side, and 12.7 is the hypotenuse. The trig function that uses opposite and hypotenuse is sine. So sine of 34 degrees and 30 minutes equals A over 12.7. If I go a step further here with my algebra, if I get A by itself, I can multiply both sides by 12.7, and that will give me what the measure of side A is. So here on our calculator, we have 12.7 times the sine of 34. I'm just going to put 34.5. 30 minutes is half of a degree, so I'm going to go 34.5. And when I do that, you can see that the measure of side A is about 7.19. Coming back to that, so 7.19, go the same decimal place as the given data, so 7.2. So side A is 7.2. We'd repeat the process for B. In this case, we'll use the same information, the hypotenuse of 12.7 and the angle. We want to use the given information as much as possible because you already saw that we rounded the 7.2, so we don't want to use that. We might create a larger rounding error. So in this case, we have adjacent and hypotenuse. So the cosine of 34 degrees and 30 minutes is going to equal B over 12.7. We'll do the exact same thing. I'll get B by itself by multiplying both sides by 12.7. which will cancel the 12.7 on this side, get B by itself, and we'll type that in, 12.7 times the cosine of 34.5, and side B is going to be about 10.466 or 10.5. So there we have solved our triangle for the two missing sides and the missing angle. Moving on to one more version of that. Notice here we have our right triangle ABC. C is our right angle. In this case, we have side A to be 29.43 and side C to be 53.58. I'm going to think that most of us would agree to find side B. The easiest thing to do would be to use our calculator and do the Pythagorean theorem. So I have 29.43 squared plus b squared equals 53.58 squared. And we'll go ahead and plug that into our calculator. We have 29.43 squared, which equals 866.1249. We have 53.58 squared, which is 2870.8164. So I'm going to subtract the 866.1249 from that, and then take the square root of that, and that would give us the measure of side B to be 44.77. Okay, so there's our Pythagorean theorem. Probably worked in a couple more steps than we needed to, but I hope you get the general idea. Side B, I'll put that up here, was 44.77. Now, to solve for either angle A or B, we're going to use, first of all, the given information as much as possible because this was an estimated side, 44.77. So we want to use given information. So if I look at angle A first, the opposite side is 29.43. The hypotenuse is 53.58, which tells us the sine of angle A is equal to 29.43 over 53.58. Now, if you recall, this 29.43 divided by 53.58 is an invert, or is a ratio, so we use our inverses to come up with that. On my calculator, I would do it all at once. Second sine, inverse sine of 29.43 divided by 53.58. So the inverses there will convert that ratio over to an angle, and you can see in this case our angle is going to be about 33.3 degrees. So angle A, back up here with our label, angle A was about 33.3 degrees. And now that we have angle A and B should add up to be 90, so angle B is going to be 90 minus 33 point, let's get rid of that point there, 33.3 degrees. And if we do the math there, angle B is going to be about 56.7 degrees. So there's our two missing angles and our missing side. From here we transition into some word problems. Pat Porterfield knows when she stands 123 from the base of the flagpole, the angle of elevation of the top of the flagpole is 26 degrees and 40 minutes. Her eyes are 5.3 feet above the ground. Find the height of the flagpole. In this case, you can see our diagram is already drawn out for us. We're trying to find the height of the flagpole, which is side A. We know the base here of our triangle, which is the distance Pat is from the flagpole, will be 123 feet. So in relationship to our 26 degree 40-minute angle, side A is the opposite side, side 123 is the adjacent side. That is a tangent function. So the tangent of 26 degrees and 40 minutes equals side A over 123 feet. That will allow us to solve for the length of A. When we get that, we'll add 5.3 feet to it. So I will multiply both sides by 123 so I can get A by itself. Going to the calculator then, I have 123 times the tangent of 26 plus 40 divided by 60, and it tells us A is about 61.77 feet. A is 61.77 feet. We have to add the 5.3 feet that Pat is above the ground. So we're looking at about 66.07. Oops, let's try that again. 67.07, or the flagpole is about 67 feet tall. First word problem. Let's move on to the next one. From the top of a 210-foot cliff, David observed a lighthouse is 430 feet offshore. Find the angle of depression from the top of the cliff to the base of the lighthouse. Drawing angle of depression, measure from a horizontal line down to our line of sight. Our cliff is 210 feet tall. The lighthouse is 430 feet away. Noting here that our cliff and our horizontal distance make a right angle, so we do have a right triangle. Now, if we recall from our work back in Chapter 1 or some geometry stuff, my water and my horizontal line up here are parallel lines, so this line cutting through here is a transversal, which simply means that the angle of depression is the same as angle B, alternate interior angles. The angle B is the same as the angle of depression, so we can find angle B by using the tangent, because if I look at tangent, I know the opposite side, which is 210 feet, and the adjacent side, which is 430 feet. That will allow me to solve for angle B. We'll plug that in. We're realizing that's a ratio, so we use our inverses. Second tangent of 210 divided by 430, and that gives an angle of about 26 degrees. So angle B is about 26 degrees, which means our angle of depression is also about 26 degrees. Let's try the next one. Zipping through a handful here where we have to make our own diagram. Kite on the end of a 250-foot string is an angle of 35 degrees above horizontal. How high is the kite above the ground? Assume the string is a straight line. As we get into these word problems, my suggestion would be to go through it piece by piece to make our diagram. Our kite is on the end of a 250-foot string. So I assume our kite is flying 250-foot string here. The string is an angle of 35 degrees above horizontal, so horizontal would run this way, and that would make our angle of our string here 35 degrees. We want to know how high the kite is above the ground. Well, height is always measured as a vertical height unless specified otherwise, so we'll call that x. If I continue my horizontal line over, here is a right angle. So we have a right triangle, which we need in order to solve these. If you look at this then, in relationship to our 35-degree angle, we have opposite and hypotenuse. I hope we all agree that's sine, so the sine of 35 degrees equals x over 250. And from here we have a little algebra, multiplies both sides by 250. And that will allow us to solve for side x. Plugging that into our calculator, we have 250 times the sine of 35 degrees, and that gives us the height is 143.39 feet. So our kite is about 139 feet above the ground. For safety and noise abatement, landing aircraft are required to be 1,500 feet above the ground. They are 25,000 feet from the end of the runway, a horizontal distance. What is the angle of the glide slope that makes this possible? Well, let's go back piece by piece. The aircraft are required to be 1,500 feet above the ground. So 1,500 feet is a vertical distance above the ground. When they are 25,000 feet from the end of the runway, so let's put the runway over here, a horizontal distance of 25,000 feet, and our plane is flying into the runway right here. So we want to know what the angle that the airplane has to come into the runway is. I'll call that x degrees. So again here, looking at our angle, opposite side, adjacent side, that is the tangent. So the tangent of angle x is equal to 1,500 divided by 25,000. And this is something we can plug into our calculator very quickly. We have a ratio, so we use our inverse tangent of 15 100 divided by 25,000 should get us a small angle, and it is 3.43 degrees. So we come in, we want our plane coming in at a too steep of an angle. So our plane is coming in at a very small angle of 3.43 degrees. Couple more to get through here, maybe just one. Airplane's distance measuring equipment measures the slant range distance from an aircraft to a navigational aid. If an aircraft with 17.56 miles slant range distance from a navigational aid is flying 2 miles above the ground, what is the distance along the ground from the airplane navigation aid? Do not use the Pythagorean theorem. First statement back here, our aircraft is 17.56 miles slant range distance from our navigational aid. Navigational aid here, airplane here. Next statement says our aircraft is 2 miles above the ground. So if we were to draw a horizontal line over here, that would make our right angle. Since we're not going to use the Pythagorean theorem, let's label this as angle A. We'll find angle A first by saying the sine of angle A is 2 over 17.56. Once we have that angle, angle A, then we can use it to find our missing side, which I'll label X. But let's go back over here to angle A. Our calculator can bring that ratio to an angle. Second sine of 2 divided by 17.56. So again, noting that we're using our inverses, inverse sine, second sine, and that converts us to an angle of 6.54 degrees. So I have angle A to be 6.54 degrees. If I want to find side X, I have choices. I can do opposite over hypotenuse, which is tangent, or I can do adjacent over hypotenuse, which would be cosine. Just to show some algebra, I'm going to do tangent. So tangent of 6.54 degrees equals 2 over X. As you've seen with our previous problems, if I multiply both sides by my denominator, that removes the fraction. So now I have X times the tangent of 6.54 degrees equals 2. I want to solve for X, so I'm going to divide by the tangent of 6.54 degrees. And I'll show that on the calculator then. X is going to equal 2 divided by the tangent. Now, what we like to do is use the given information, or we don't want to round any more than we have to. So I'm going to pull this 6.539906934 back up by using second answer here. That way I use the entire angle instead of rounding to 6.54. And that tells me my aircraft is about 17.45 miles above, or horizontal distance away. 17.4457 or 17.45. So the long way around it gave us a look at how to use our trig functions. Now, like I said, we could have used cosine as well. We could have said the cosine of 6.54 degrees equals X over 17.56. In this case, we multiply both sides by 17.56, so these canceled. And I'll just show you how that winds up being the same thing. 17.56 times the cosine. I'm not going to bring the whole thing back up here, 6.54 and 17. Pretty much the same number, 17.4457. So the first 4 digits were the same. Okay, so a couple different ways or trig functions we could have used to solve for that particular missing side.